Okay, so the recording has started. So, do you people have any queries from the last week session? Anyone have? You may message me as well. Okay. Okay, then we will wait for 1 more minute and then start. Okay, then. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL PMF teaching assistant for the course Introduction to Probability Theory and Stochastic Processes. This course is offered by Professor S. Dharmaraja. He is a professor in IIT Delhi. So this is a 12-week course, and we are in the second week of live session. I hope you people have watched the videos for the week 2. If you people have any kind of doubt related to anything regarding the course or any other material, then you people directly may ask. Okay. So yes, Nikhil, do you have any query? Okay. So this is week 2. Okay, so in the previous week, we have discussed about the basics of probability. Okay, so in which we discussed the random experiment, the definitions of probability, the sigma field and sigma algebra, both are similar, equal actually. And then there are three definitions of probability, like the classical or mathematical definition. The second one is the statistical or empirical definition. And the third one is axiomatic definition of probability, which was given by Kolmogorov, Russian mathematician Kolmogorov. Okay. There are three axioms in that definition actually. Then we have also discussed about the conditional probability and a specific form of conditional probability that is called the Bayes theorem. Okay, so that was the week 1. In week 2, we will mainly discuss about the random variable. Okay, the random variables, its definitions. Then we will discuss about cumulative distribution function. Then we will discuss about cumulative distribution function in abbreviation form. Usually we will write CDF, random variable, or RV. Okay. And then there are types of random variable is there. Types of random variables. And with related to these types, we have probability mass function. Then we have probability density function. And then we discuss about the transformation of random variable actually. That is also called distribution of functions of n. Is distributions of functions of random variables. Okay, so these are the topics which have covered in week 2 lesson. So we will just take a snapshot and then we will solve some numericals based on these topics. So let's start with random variable only. Okay. So can anyone want to define what is random variable? Anything related to random variables? See, a random variable, as its name suggests, it is not a variable first. Okay, it is a function actually. A random variable is a function which maps uh, the sample values which is associated from the sample space. Okay, so the value, like it actually define a map, a function which takes the which input from the sample space and give output as a real number. Okay, so it's a function which map the sample values to the real number or real line. Okay, so that is called random variable. Okay, it is a function. Why we call it a random variable? Because uh, it actually associated with the random experiment. So from there, it is called random variable. Okay. So the actual standard definition is like, let me write this. Let me, we are given omega, f, and p. This is the probability space. Suppose this is a probability space. Okay. Then a real valued function, a real valued function, uh, let me write it x. X is a function which map from the sample values, from the sample space omega to the real line, the real number. Okay, is said to be a random variable if if since it is a function. Okay, so it's inverse function, x inverse. Okay, so it's inverse function which is from the real number, obviously. So let me write minus infinity to x, the open interval minus infinity and the closed interval near x. Okay, so this must belong to the same algebra, the sigma algebra. Then only we say that this x is a random variable with respect to the sample space and the corresponding sigma algebra. Okay, so this is the standard definition of random variable. For the for making some kind of image related to the random variable, you may directly can understand via this slide. It is a map, it is a function which assign a number, real number for the sample values. Okay, we will solve some numericals like when we toss 2 coins, when we toss 7 coins, when we toss 500 coins simultaneously. We can't say anything about the outcomes. Okay. But if we assign a real number related to those outcomes, then we have some comparative study. Okay. So this is a kind of converter variable function, not variable function, that is a random variable. Okay. So this is actually the definition of random variable. When we will formulate any kind of random variable, then we will check whether that function, that random function, is actually a random variable or not with the help of this definition only. Okay. The next is we have some remarks actually. Okay, these are already discussed in the lectures. Okay. So, like a real value, it is a real valued function, as I have told. Like here, it is also already written a real valued function. Okay, but it is called a random variable because it is defined over the sample space, which is constructed via a random experiment. So that's why it is called random variable. Also, it is a measurable space. Okay, measurable function over the given sigma algebra that we have defined here, F. Okay. Also, let me write an example. Okay, I'm not going to write the remark. Just tell you the remark. So let's start with an example. Okay, suppose we are given a sample space having 3 elements. I'm taking 3 elements because 2 element is quite less amount of element, and if we are taking 4, then 2 to the power 4 have 16, which has like 16 number of elements in the uh, power set, you may say, or the sigma algebra. So that's why we have taken the 3 cardinal T sample space. Okay, so it has 3 elements. Now, as we know, okay, as we know, there is some empirical, sorry, not empirical, it's trivial. Trivial sigma algebra is there. That is the phi and the this. This is the trivial sigma algebra. We have already discussed. Okay. Besides this, we have also different kinds of sigma algebra, and the largest sigma algebra is the power set related to this omega, which has 8 number of elements. But let me define some other sigma algebra. For example, phi, A, B, and C, and omega. Okay, it is also one of the sigma algebra. If we can define this also, these all are having 4 cardinality actually. F3, it's AB. And you may define more number of sigma algebra related to this over this sample space omega. Okay, so we will focus on F1 here. Okay, now we will define one random variable. Okay, we will define a function, and the function is like we define a function. Let me write the random variable instead of function. Oops. We define a random variable x such that x is a function from this omega, this f1. Sorry, not f1, it's r. Such that x of omega equals either 0 or 1. When it comes out to be 0, when omega equals a, when omega equals b or c. Okay, so this is the function. We define a function x omega via this. Okay, now we need to check whether this x is a random variable or not. This function is random variable or not. So let's define now. See what we are going to check whether the given x function, the x omega function defined over this sample space omega is a random variable or not. For this, what we need to define the inverse function, and it is like minus infinity to x. Okay, so this function will be like something. So we have 0 and 1. We have only 2 values for this. So we can like partition this in 3 parts, like less than 0, 0 to 1, and more than 1. These 3 parts are only there. So the first one is x is less than 0. The second one is 0 to 1. And the third one is x is greater than or equal to 1. Up to this point, it is okay. Na? Since x omega function contains only 2 values, 0 and 1. So we can partition this in 3 parts, less than 0, 0 to 1, and more than 1. Okay, I have written here like that. Now, if I'm going to like write this, since it is 0, na, so here it comes out to be 0, here it comes out to be 1, and then so on. Okay, so now for x is less than 0, for x is less than 0, then obviously the any kind of number comes out to be less than 0, maybe here or somewhere here between minus infinity to 0 only. And since 0 is not included, So for that, we do not have any kind of definition. X omega doesn't contain anything. So that means we have nothing but the pi, empty set. There is no element associated with this range, minus infinity to 0. Okay. So this is the case. Now the second is 0 to 1. If I'm going to take any value lies between 0 to 1, including 0. So let me take here. Okay, this value. Okay, let me, for example, for it's, let me tell it x1, it's x2. Okay, this x2 equal to actually lie between 0 to 1 or before 1. Okay, so that means x1 lies before 1, x2 lies before 1. Okay, and that simply means this 0 is included here. Okay, so that means the value associated with this is 0 is actually A, the singleton set A. And in the same manner, if if I take the value 1 greater than 1, or okay, the value of x is greater than, or this can also be written as like 1 x infinity, that means all values. So all, obviously you can see that all omega comes out to be here. Okay, so these three are like, we can define the inverse function of this given function x omega. Up to this point, it is okay. Okay. Now the next step is to check whether this all belongs to f or not, because here we define this belongs to f. This belongs to f. So let me check whether these belongs to f or not. So yes, you can directly see now. Here this always belong to f. Okay. This we are taking actually one f1. We are taking f1. So yes, a is belongs to this, and this can also. Okay. So that means x inverse function belongs to this cursive f. So what we conclude? So we conclude that x is a random variable. Okay. X is a random variable for sigma field. Okay. Sigma field uh, f1. Okay. Now this is the question. Okay. Now you people understand what we are doing actually here. These are actually like just a simple function. We define the inverse function. Okay. We now need to check whether the values from this inverse function belongs to the field f or not, sigma field f or not. So here it's f1 actually. Okay. So we have found that all the elements belongs to the f1. So that means we can directly say that with the help of the definition of random variable, that given function is random variable. Okay. The same thing happens. Okay. For another random variable as well. Okay. Now let me take another example. Okay. We will define one more random variable y. Now, this random variable y is something like 0 and 1 only. Okay. So it's omega equals b, and omega equals either a or omega equal to c. Okay. The same thing, only we will, what we are doing, we will define for y equal to 0 when omega equals b, otherwise a and c for 1. So again, we are doing the same thing. We define the inverse function of y. Again, it's minus infinity. Let me write it 0, 1, and plus infinity. Okay. So the first thing is 0 and 1. So x So x is less than 0, included 0, and x is greater than or equal to 1. Okay, these three conditions as we have already discussed in the x inverse case. Now, x is less than 0, have somewhere this point. For that, there is nothing element is defined, so phi is there. Now, for 0 to 1 included 0, let me, I need to write y, no? Okay, so it's y1, it's y2. Y2 can take any value lies between 0 to 1. It includes nothing but the only element related to 0, that is b. And for that, we will find this value. Okay, so from here, you can see or you can observe that this belongs to obviously F1. This belongs to by default F1. Okay, but this B element, the singleton B, is not there in this. Okay, the singleton B is not there in. So that means what? So that means uh, okay. So that means what? That is Y is not a random variable. Y is not a random variable for the sigma field F1. But on the same page, you can see that F2 contain B. So that means I can claim, I can claim, I can claim but Y is a random variable for sigma field F. Okay. On the same hand, I can't claim that y is a random variable for F3. Okay, so that means you can see na, कि some sigma algebra is random variable. Sorry, some function, some random variable. Sorry, let me rephrase. Okay, for some sigma field, one variable is random variable, on other is not a random variable. Okay, that we can claim. So we have a question like, is there any sigma field that is actually a random variable for all the function defined over the same omega sample space? So yes, there is a function. Sorry, there is a sigma algebra which is for which actually a random variable is a universal kind of random variable, you may say. Okay, this is actually one of the remark here. Okay, you can see we can define any other random variable z here. Okay, which is associated with F3. You can you can check if z defined in such a manner that z equal to it's like 0 or it's 1 when in the same 0 when omega equal to nothing but c, and omega equal to either a or omega equal to b, then obviously z is a random variable for z is a random variable for f3. Okay, but is there any sigma field? So yes, we can have a sigma field f. Let me write. Yes, this remark is like this. Let me write in the remark form. Okay, the any real valued function that any real valued function any real valued function will be a random variable, okay, with respect to the largest sigma field. Okay. So for the largest sigma field, any kind of real valued function defined over a given sample space is nothing but a random variable. Okay. This is also called here the largest sigma field, as we have already discussed in the last class. The largest sigma field is nothing but our power set of the sample space omega. Okay. So in any case, if you have any kind of sample space, then you must if you want to create any kind of random variable, then take the power set of that sample space as your sigma field, and then you will nothing worry about these kind of thing like hereby is not a random variable for f1, but for f2 it is a random variable kind of situation. Okay, so this is actual beauty of the largest or the sigma field. Okay, any doubt up to this point? Anything you people want to ask? This is the random variable. Okay, now we have a distribution function. So see, distribution function is not actually associated with the probability. Okay. Most people think like we need to use a probability to define this. No. Okay. This is how something is distributed. This function actually gives this kind of information. Okay. So it is also a real valued function. So a real valued function, usually we will denote it with capital F or capital G. Okay. So F satisfying the condition. Okay. So we have actually four conditions. Okay. The first one is like if this function must lie within 0 to 1, including both. Okay. The second is it is actually monotonically non-decreasing. Somewhere you may find that it is monotonically increasing, but actual or the correct is non-decreasing. Okay. Monotonically non-decreasing function, it must be. It simply means like if x1 is less than x2, this implies what? The functional value of x1 is always less than or equal to the functional value of. Okay. So this is the meaning of the monotonically non-decreasing function. The third one is the limit. The limit of x tends to, it's like minus infinity. When we apply limit over this function, it gives 0, and limit x tends to infinity, capital Fx give 1. Okay, so that means it covers the range. Here also keep this in mind that here this minus infinity and this plus infinity is not actually infinity. It is the terminal values of the support. The support is like the random variable x. Okay, all the possible values of random variable. So the minimum value and the maximum value is nothing but here denoted as minus infinity and plus infinity. Okay. So and yes, the fourth is this function must be continuous to the right. Okay. It is right continuous function. Okay. The continuous to the right means is like limit like x tends to 0 plus fx equal to the functional value of this. Okay. Sorry. So these are the four conditions. Suppose a function f which follow these four properties, then we say that that function is nothing but a distribution function. Okay. Now we will solve one example, and we first define a random variable, and on the basis of those random variable, uh, we will construct the distribution function for that variable as well. Okay, and then we will solve numericals based on all those terms. So please ask, okay, every time if you people face any kind of doubt or confusion, directly you may interrupt. Okay, like for example, let's take uh, the rolling a die example or tossing a coin example. So the tossing two coins simultaneously example has been discussed in the literature, in the lecture actually. So we will discuss those topics. So like let we toss two coins. Okay, we will toss two coins simultaneously. Obviously, then in that situation, our sample space will be like either two head occurs or the first one and the second tail, the reciprocal or the inverse tail and head, and then both tail. Okay, these are the case. Now there is one more. We have sample space. The next thing we need is actually a sigma algebra. Okay, so as we have like written here as a remark, na, we will take the power set. Okay, we will take the power set. So the power set of this is like we will take f, not going to write f1. We will take f as the power set of omega. It contains the values like the phi is there. Okay, then the singleton elements are there. It's HH, then HT, and then TH, and then TT. The four values is this. Then it contains the two values together at a time. Okay, so it's like HH and HT is there. Then HH and TH is there, and then obviously there are six possible cases for two. Then it contains three elements at a time. Okay, it's like HH, HT, TH, then again, and at last it contains all the four together, which is nothing but our sample space omega. Okay, so the cardinality or the number of elements in this F is nothing but it's like number of element in this is nothing but 16, which is 2 to the power 4 because it contains four elements. Then the uh, number of elements in the power set is 2 to the power 2 to the power n, here n equal to 4, so 2 to the power 4 is the okay. So this much of elements is there. Okay, now we will define a random variable. Okay, now let's define a random variable x from this omega to r. Okay, which type of okay, so let me define a random variable here na. Since we are tossing two coins together. Okay, we are tossing two coins together, so which type of random variables we can assume? Like if we are focusing on the number of heads, it's number of head. So the possible values of number of head is either 0 or 1 or 2. If we focus on the number of tails, it's again 0, 1 or 2. Okay, and there is no other option like we can define, or we can define any other kind of thing, but these are basically two simple random variables we can define. Okay, so x is what? X is number of heads. Okay, so that means what? The possible values of x is 0, 1, and 2. Okay, the possible values of x is either 0 or 1 or 2 because there is no head, there is one head, or there is two head. Okay, so this is the case. Now we need to define the function form, that is x. So obviously we have either 0 or 1 or 2. So number of head is 0, belongs to nothing but this elements only, no? Because here there is no head occurs. Number of head is 1, it's either HT or it's TH. Okay, so 2 is there actually. Omega is either HT, omega is either TH, and 2 is again nothing but HH because all the two elements gives head. Okay, so this is the function we have defined. Now our aim is to check first whether this x function we have just defined is actually a random variable for this sigma algebra f over the sample space omega or not. This is our first aim. Okay, so let's check whether this given x is actually a random variable for omega, sorry, for f or not. For that again, like to check whether x is random variable for f or not. Okay, so as we know, x inverse function again it's minus infinity to close interval x. This must belong to the f only. So let's define okay x inverse of. So see here. Here we have three possible values of actually x, na? 0, 1, and 2. So this implies what? This implies we can partition it in four parts. Less than 0, then 0 to 1, then 1 to 2, and then more than 2. So we can part it in four equal parts, not equal, four parts. So that means what? That means the first one is 0. Yes. So x is less than 0. The second one is including 0 and excluding 1. The third one is it's including 1, excluding 2, and the last one is greater than or equal to 2. These are the four parts we can define. Okay. Now the next step is just again the same kind of thing. Okay, let me draw a real line here. Here it's minus infinity. Okay, it's 0, it's 1, it's 2. Okay, here comes out to be some infinity part. Okay, now what we can do is less than 0. So for less than 0, we do not have anything because less than 0, if you toss a coin, then either 0 or 1 or 2 is possible. So again, it's 5. 0 to 1. 0 to 1 includes 0 only. So 0 means there is only 1. So yes, this belongs to only here. It's double there. Okay, like 10. 1 to 2. 1 to 2 is excluding 2 contains actually what? Head, tail, or tail head for x equal to 1. And also, since less than 1, 2 is there, so that means tail and tail is also there. So that means what? It's tail, tail. Okay. Let me write like this. It's head, tail, it's tail head. Okay, and at last less than, sorry, greater than or equal to infinity, like that. So that means what? Head is there, head tail is there, tail head is there, and tail is there. That means all the functional values, the outcomes are there. Okay, that means the sample spaces. Okay. So that means this is our functional. Now the next step is to check whether these belongs to f or not. So yes, this belongs to f, this belongs to f, this belongs to f, as you know, the all singleton set from those. And yes, when we extend this now, then HT is also there in one of the form. So yes, this also belongs to the. So that means what? This x inverse function actually this belongs to. So that means yes, the x is a random variable. Okay, that's simple, no? You just need to check this and to claim whether this is a random variable or not. Okay. So yes, it is a random variable. So now what? Now our aim is to define the first step is complete actually. Okay. We have proved that or showed that this x, the function defined here is nothing but a random variable for omega for the sigma algebra f. Now the next is to like construct the distribution function. Okay, so as we know the distribution function fx, this is usually the standard notation that here x follows some kind of distribution or something. So with the distribution function capital X, capital F, sorry, capital F. So obviously you can see the functional value of x is what? Less than 0, 1, 2. So we have only three values. Okay. So the first one is less than 0. Then you can directly write this actually. Less than 0, less than 1, x is greater than 1, x is greater than 2. Okay. We write okay, 0 to 1 is there also. No? Let me write in that way. So x is less than 0, 0 to 1, 1 to 2, and x is greater than or equal to 2. These are all the four cases that we write here. Okay. So for this, x is less than 1. How many elements are there? 5 is there. So obviously, this functional value is nothing but 0. For 0 to 1, including 0, it has only 10. So out of the four possible outcomes, we have only one outcomes is there. For 1 to 2, like for 1 to 2, actually, its definition is something like this. Okay, let me write the definition again. Fx is equal to nothing, probability that x is less than or equal to x. Actually, this is the definition of the distribution function. Okay, so here 2 less than 2 also includes 1, 0, and all. So that means the total number of elements is 3. L, L, add L, and tell L. So this implies it's nothing but 3 by 4, and for 2, it's obviously 4 by 4 comes out to be 1. So this is our distribution function defined for the omega f space. Okay. So this is how we can define. You can check actually if you want, you can check whether we define this function, this fx function is actually a distribution function or not. And for that, what we need to do? We need to check. We need to check these four possibility. No? We define just a function. We just define a real valued function there. We need to check that if fx value lies within 0 to 1, it must be monotonically non-decreasing. At limit this kind of existence there, and yes, it is right continuous. So you can see actually if you want, you can see here directly without like writing much. The minimum value is 0, comes out to be 0, comes out to be 0, and for maximum value comes out to be 1. So yes, that is the third one is actually, this one is third one. The first one is it's lie within 0 to 1. So this fx actually lie within 0 to 1. So yes, this lie within 0 to 1. The second one is monotonically non-decreasing. So you can directly even see this via graph or plot. Like here, no? Less than 0, it comes out to be 0. So that means what? Something here like, no? It's 0. Okay. Then from 0 to 1, it's 1 by 4. For example, it's 1 by 4 is there. It's it's 0, it's 1, it's 2, 3, and so on. From 0 to 1, it's 1 by 4. And from 1 to 2, it's 2 by 4. And then it's 3 by 4. And then it's 1. Okay. So it's 1 by 4. And then from 1 to 2, it's 3 by 4. It's 3 by 4 is something like this. And from there to 2, it's okay. From 2 and onwards, it's 1. So yes, you can see that it's a non-decreasing function, obviously. Okay. And also, it is continuous to the right. It is also continuous to the right. And yes, continuous to the right means what? Continuous to the right means it's like limit x tends to positive, like 0 positive. Okay. This value is actually, if we can write like this, it's like f of x plus h, which is actually f of x, for x is equal to obviously 0. Okay, this condition actually holds. Any value for this, like you take x equal to like 1. For example, take x equal to 1, then this value. For any value greater than this is actually the same value, no? The same functional value 3 by 4. So that means it is continuous to the right. So this capital Fx follow uh, all the four conditions for the distribution function. So yes, it is a valid distribution function. Even in examination also, we can directly ask these kind of things, whether we are given some function and we need to check whether this random variable is an actual random variable or not over the given field. And this function, this given function, a real valued function defined, is actual a valid distribution function or not. Then in that case, you need to check those four qualities. If any of those four qualities is missed, then that is not a valid distribution function. Okay. So this kind of question we have already solved many times in our exam during our classes. Okay. So this is it. Up to this point, you people have any doubt? If not, then we have 2 or 3 more things to discuss. Okay, like the types of random variable is there. Types of random variable. Okay, so it is mainly of 3 types. Okay, when the support is defined in such a way that there are jump points in between them, that is then in that case it is actually discrete random variable. Okay, when we have a continuous function kind of support, then we say that it is a continuous random variable or continuous type random variable. And there is one more case when a function defined is like have probability values at discrete at some particular point, some jump point, as well as some interval. Okay, so in that case, it is called mixed kind of random variable. That is, if some values contain some probability values at some jump point, okay, so discrete nature at that point, and in some range, in some like interval, it has a like continuous nature. So that it is called mixed random variable. I'm not going to like write those things. Okay. The probability density, the probability function, actually the probability function associated with the discrete random variable is called uh, probability mass function, PMF, probability mass function. And again, for the continuous case, it is called probability density function. So that means probability density function and probability mass function are the same function. Okay, are the same function, just the terminological differences related to the discrete random variable and the continuous random variable. Okay, if I'm like saying, usually we are saying PDF or probability density function for the in general term, but actual term that we must need to use is for discrete random variable kind of thing. We always use the probability mass function, and for continuous probability density function, or in general we use density function. Okay, even in further classes, it may probably I missed that probability mass function. I usually use the word density function. Okay? I think someone has messaged something. Okay, no. Okay, which kind of no? Sorry, I'm not able to like. Yes, let me know. Or what question you are saying? No. Okay, you type asking any doubt. Okay, okay, thank you. Okay, then we also have let me write 3 more thing actually. 3 more just statement kind of thing. Okay, the first one is like you need to find the probability. Okay, if we are given the distribution function and then we need to find the probability of a random variable x lie within the values a to b, including b, excluding a, is actually defined as fb minus fa. Okay, this is the first condition. There are two more. If we include a and b both, if we include a and b both, then in that scenario, it's fb minus fa. Since A is not included in the first one and included in the second one, so in that scenario, we need to subtract the probability value at that point only. That is probability that x is equal to A. Okay, and there is one more, the last one. If both are not included, A, X, B. Obviously, you people can understand the logic here. Okay, from first and from second, you directly write the third because here, like what? B is not included. No? So it's FB minus FA is there. Okay. So if B is included, then this. If B is not included, then we need to, here it is not equal. No? So we need to minus probability that equal to B. Is it okay? I think it's clear. No? If only B is there, this is the standard formula. Okay. This is our standard formula. If A is included in the second one, if A is included, then we need to subtract the probability value at that point only, that is probability that x is equal to A. And if A is not there, so this already contains this value, star, so minus of probability that x is equal to B must be subtracted from there. Okay. So these are the things. And yes, there is a last theorem that is related to the distribution of functions of random variable. Okay. So it's like, yes, it's like suppose we are given a random variable x and we construct or we transform a new random variable with the help of the old random variable. Then the distribution of functions of random variable is that. This situation is called distribution of functions of random variable. Somewhere in user notation, we call it the transformation of random variable. Okay. So we transform the random variable from x to some other y or z or some other random variables. So for that, suppose we are given a random variable x, we write in a theorem form. Okay, suppose we are given a random variable x and we are given a transformed variable y, which is actually defined with the help of the random variable x. Okay, so this is y variable and this is x variable. Since the initial variable is x, we have x random variable. Okay. So we have x random variable, and then we need to find this x is associated with the probability density function or probability mass function depending on the nature of the x. For example, usually we will use density function as we have already discussed. Okay, so x follows a density function fx. Okay, so we need to find y, which is actually a function of x, follows which kind of distribution. Okay, so for example, I can write fy. Then I need to write the value of y with the help of x, the distribution of y with the distribution of x. Okay, so there is a actually definition. Okay, when here this g function is, if this gx is strictly monotonic function, okay, and this is differentiable. If these two conditions holds by this transformed equation y equal to gx, then we can directly use this formula. The density function of random variable y is actually the density function of x. Here in subscript, we have written x of g inverse y. G inverse y is nothing, just here from here y equal to gx, that is g inverse y equal to x. Okay, so x can be replaced here by g inverse y. Okay, G inverse Y, and this is multiplied by actually ddy of G inverse Y. That is dx upon dy kind of structure. Okay, this is the Jacobian part or zero otherwise. Okay, so this is the case. Okay, this is the theorem actually. We directly use this formula if gx is strictly monotonic function and differentiable function. Then directly use this formula to find the distribution or density function of the new random variable. So these are up to this point. If you people have any question up to this point, you may ask. Otherwise, we will solve now numericals based on these topics. Okay, then we will solve some numericals. See, there are simple questions and there are some questions which is maybe you people don't get by yourself only. Okay, so now the first question is consider a random variable x. It given a random variable x that has a PDF, that has a probability density function which is PDF. Okay, given by, we are given the function is like when x lie within 0 to including both and otherwise. The correct or right way to write the PDF is actually this form. Okay, always write like here kx lies the fx value equal to kx or x lie within 0 to 2. This is x lies between 0 to 2 is actually our support system. Okay, it is our support actually. Beyond this, the definition is not valid. So it comes out to be 0, otherwise 0. So overall, if you like forget to write the support, then it is not a valid probability density function, because probability density function has properties. The integral values of this PDF over this support is actually comes out to be 1. If you miss the, okay, I think someone please repeat the theorem. Okay. Okay, see, suppose we are given a random variable x. Okay, now we and this x follows the distribution fx. This x follows the distribution, the density function, which is fx, denoted as fx. Okay, and you need to find a transformed random variable. You need to find the distribution or density function of the transformed random variable, and that random variable y is actually defined over the same random variable x. Then we can directly find via this formula. Okay, we can directly find the density function of the transformed random variable y via this formula if this transformed random variable follow strictly monotonic function and it is differentiable. And in that case, we can directly use this formula to find the density function of the transform or new random variable. Okay, this is the simple. We will solve some numericals actually. Then it is more clear. If still you have doubt, then you can let me know again. Okay. So now, yes, we have this question. We have a random variable this. We need to, okay, yes. I'm telling like this, we always need to write, the support with the PDF so that it must be so that it is a valid PDF. Okay, usually we forget to write, but it is not the correct practice. Okay, for the standard practice, you need to write the PDF together with their support. In the next week, obviously, we will discuss about the discrete and continuous kind of random variable. There you can see for binomial distribution, the support starts from 0, 1, 2, 3, 4, up to n, predefined value of n. But for Poisson, we again start from 0, 1, 2, 3, 4, but it goes to infinite. Okay, so there's a difference. if you are not going to take for n for Poisson case, you take the value up to n, then it is not a valid PDF. And it is not actually Poisson distribution. Okay, so always try to write this, make this in practice. Okay, now our question is to find the value of k actually. We need to first find the value of k, find the constant k, also find the probability that x lie within 0.6 to 1.5. You may also like construct some questions by yourself even. So let's first find the value. Okay. So since it is a valid PDF, if it is a valid PDF as it is stated here, so it must follow some properties. Okay. The first or the main that we are usually used is like if fx is a valid PDF, probability density function, then the integral over x fx dx comes out to be 1. Okay. So that means what? So integral over here, the support is here 0 to 2 and the PDF value is kx. So the integral of kx over the range 0 to 2 dx comes out to be 1. Simple. That's nothing, just an integral. No? K is taken outside, x comes out to be x square by 2. It's 0 to 2 comes out to be 1. From here, like k by 2, it's 2 square comes out to be 4 minus 0 by 2. This obviously k comes out to be 2 without like sending this steps. Okay, k comes out to be okay. Is it okay? Anyone? No, it's not okay. It's 1 by 2, no? Because 2 times of k equals 1. So that means k equal to 1 by 2. So our like appropriate or valid PDF is comes out to be kx. That is x by 2 for x lie within 0 to 2 and 0 otherwise. So this is our valid PDF. Okay, someone has messaged again. Yes, it's 1 by 2. Okay, so up to this point, it is okay. That means, okay, everyone got it that it's 1 by 2. So the next is we need to find the probability that it lies 0.6 to 1.5. Okay. Okay. Then what next is? We can see that no, 0.6 to 1.5. So obviously it is a continuous. So we will directly use integral from 0.6 to 1.5 k x, it's x by 2. Kx is x by 2 and dx. So it's simple. No? It's 1 by 2 is there. It's 1 by 2 is there. Sorry. And then it's x square by 2, 0.6 to 1.5. It's 1 by 2 is there. So we can write it like it 1 by 4 to 1 by 2 is taken common. So x square. So 1.5 is square minus 0.6 square. So it's 1 by 4. It's 1.5 square comes out to be 2.25 minus 0.36. So let me know the exact answer. So it is 36, 1.89. So 1 by 4, oh sorry, 1.89 divided by 4. Okay. So obviously the probability that x lie within 0.6 to 1.5 is, let me know because I do not have written the answer here actually. It's 0.5, 0.4, 0.4. Anyone is 4725. Okay. 4725. 0.25. Is it okay now? Because I have done up to this point only in my sheet. Okay, so 0.4725 is probably the answer. 4K45980. Okay, yes, it is possible. Okay, then. So it's 0 point. So this is the correct answer, I guess. You can directly, like, what is the probability that lie within -2 to 5? Can anyone let me know what is the probability up to this? What is the probability that x lie within -2 to 5 when the PDF is given like that? PDF is x by 2 or x lie within 0 to 2. Okay. We need to calculate the probability that -2 to 5. Okay, you can solve. Okay, okay, 0. So Nikhil said it comes out to be 0. Okay, just try to. Okay, someone another. Okay, and Rashmi said it comes out to be 1. Okay, so you two people have said two possible values, either 0 or 1, obviously. Okay, let's see. Uh, that is probability is -2 to 5 is like what? It's minus, see here first. The support is 0 to 2 only. Na? So we need to keep that in mind. 0 to 2. So -2 to 0. Let me first -2 to 0 plus probability 0 to plus probability 2 to 5. Okay. I can like partition this probability into these three parts. Okay. Now see this value, what it comes out to be. It comes out to be 1, na? Because it is the prob 2. How can I? Okay. See. How can it be 2? Na? Because it comes out to be 1. Na? Because it is a valid PDF now. It is a valid probability density function. From here only. Na? From here, it is a PDF value. AX is our PDF value. Okay. And we use this integral of fx comes out to be 1. From there, we find the value of k equal to 1 by 2. Okay. So that means if we take the value of k equal to 1 by 2 and integrate, it comes out to be 1. So that means this values comes out to be 1. Okay. And this value and this value comes out to be 0 because for others it defined as 0. No? So our question is like what? 0 plus 1 plus 0 comes out to be 1. Always remember the probability function, the integral or the summation. Okay, the summation or the integral of a probability function has maximum value 1. Okay, this is also one of the property of a probability distribution. Like it lies within 0 to 1. It is non-negative. Obviously, it may contain value probability as 0 and 1. If probability comes out to be 0, then it is nothing but impossible event. If the probability of any kind of event comes out to be 1, then it is certain or sure events. Usually the probability of any kind of event lie within 0 to 1 if it is a valid kind of events defined. Okay. So yes, it comes out to be 1 only. More than one probability is not exist. Okay. Always like keep this in mind. In examination, even this kind of question asked directly without if it contains support. If it contains support and other value, extra values, then obviously comes out to be 1 only. There is no other option. Okay. No need to like give much time to solve this type of question. Now let me solve the next question. Up to this point, anyone have any doubt? Please let me know. Okay. So the next question will be like, suppose the distribution function of x is given by, okay, suppose the distribution function of x is given by, like we are given a distribution function. So usually we denote it capital Fx. So it's like 0 when x is less than 0. It's 1 by 4 plus x by 2 when x lie within 0 to 1, and 1 when x is greater than or equal to 1. Always, you may always see in future, obviously, that the capital Fx comes out to be 1, and for all the support value, the maximum value x is greater than 1. So in that scenario, it the functional value of fx, the distribution function, is always maximum value comes out to be 1. Okay, this is one of the property actually we have already discussed in above, no? That it lies within 0 to 1. Okay, the maximum value gives out to be 0, the minimum gives to be 1. Sorry, the maximum value of x of fx for the max. Let me phrase my question. The maximum value of fx for the maximum value of x comes out to be 1, and the value of fx for the minimum value of x is 0. This is the property we have seen. So this is the question. Now we need to define. Okay, what is the question? I haven't written the question actually. Okay, we need to check whether this is which kind of random variable it is belong to. Okay, this is the cumulative distribution function. It is a CDF. Now we need to about find the nature of random variable x. Okay, we need to check whether this random variable x is discrete in nature, continuous in nature, or like mixed kind of random variable. Okay, so obviously we need to check here related to the jumping points, the interval only, these two, and we need to find the probability associated with the jumping point as well as the interval. If both have some kind of probability, then that is discrete as well as continuous, so it is mixed. If the probability at all the jumping points comes out to be 0, then in that case it is continuous in nature. Or in the reverse, if the probability is accumulated only on the jumping points and not in the range, then it is discrete in nature. Okay, so let's solve this. Again, let me see fx equal to 0, 1 by 4 plus x by 2 when lie within 0 to 1, and 1 for x is greater than. Okay, so yes, as we know, probability that the CDF, no, we are going to define the CDF. The CDF is actually nothing but probability that x is less than or equal to x. Okay, anyone have any doubt? You people may type and like in the chat as well. Okay, this is the definition. This is the definition of CDF. Now we have here two jumping points, 0 and 1. So let's first start at 0. So for x is less than 0, here for x is less than 0, the CDF is already defined here. The fx is 0. So that means at 0, there is, sorry, not 0, less than 0, there is no probabilities associated. Now, at x is equal to 0, fx value comes out to be like what? At x is equal to 0, it's 1 by 4 plus x by 2. It's 1 by 4 plus x by 2 at x is equal to 0. So that means fx at 0 comes out to be 1 by 4 plus 0 by 2 comes out to be 1 by 4. So yes, Rashmi has said it's mixed type. Okay, let me see. So at x is equal to 0, there is some probability associated. So that means yes, it is a discrete type at x equal to 0 up to this point. Our next step is to check see one more thing. I need to rephrase my sentence here. at x is equal to 0 comes out to be 1 by 4. It is not the probability value. It is actually cumulative probability value. Okay. So probability value at x equal to 0 comes out to be like what? Probability that x is equal to 0 minus probability, sorry, the distribution functional value at x is equal to 0 minus the functional value at x is equal to 0 minus. Okay. So this is the case. So it comes out to be like 1 by 4 minus, and fx at 0 minus is what? The less than 0 kind of thing. For less than 0, it comes out to be 0. So actual value of probability at x is equal to 0 is 1 by 4 here. So that means at x is equal to 0, there is some probability that is a discrete type of kind of random variable at this point. Now the next step is to like check whether next we need to check whether x lie within 0 to 1. Okay, 0 is already there. Okay, so like fx at 1, suppose at 1, what we can find at 1, it's 1 by 4 plus x by 2 comes out to be 1 by 2, 4, 1, 2, 3. It's 3 by 4. Okay. So actually there is some, this is the CDF value. This is the cumulative distribution functional value. Now it's equal to 1. Okay. So we need to first find the distribution function here. So density function. Okay. Let me not write this. So it's a ddx of like what? 1 by 4 plus x by 2 comes out to be 1 by 2. So obviously, without even, we do not need to like check this, or you can check. You otherwise you don't need to check that. Directly you can find the density. Okay, it comes out to be 1 by 2. When x lie within 0 to 1. When x lie within 0 to 1, in that scenario, the density function has value 1 by 2. Okay, and that means it is associated with some kind of probability. The some kind of probability is associated with this range as well. Okay, so that is what? That is this this CDF. Okay, or this random variable. Since that is x is, sorry, x has, that is x has some probability at jumping point and some probability in a given range. Okay, so this implies what? This implies x is a mixed type random variable. Okay, so this is how you may check whether this is a discrete, continuous, or mixed type. Okay, up to this point, any question, anyone? Now we will solve next question. Okay, the next question is, let x be a random variable. Let x be a random variable with probability mass function, that is PMF. Okay, we have written here like PMF, that is this x is actually nothing but a discrete kind of random variable. Okay, because then only we use the PMF. In continuous case, we use density. Okay, so PMF, what are the PMF we are given? The probability that x is equal to k is nothing but 1 upon 2 to the power k for k equal to 1, 2, 3, and so on. Okay, so here you can see all the probability is associated at the jumping point only, at the jump point 1, 2, 3, 4, 5, and so on. Not at the middle value or the like probability at 1 to 2 in excluding both. There is no probability associated with that range. So obviously it is nothing but the discrete kind of random variable. Now, okay, now calculate 64 times fx at 6. We need to calculate, this is the given probability mass function. We need to calculate the fx at x is equal to 6 into 64. Okay, that's a simple question. You people also please try to solve by yourself and then we will see answer match or not. It is a discrete, obviously, for a discrete type random variable, the CDF. The CDF is defined as actually the summation probability that x is equal to k. Here we are using k. No? So k is lies between 0 to, since there is no point, so infinity we can write. So this is our, actually our formula is like this, the probability that x is less than or equal to k. This is our formula for the density function, for the distribution function. Okay. So this is our formula. We are taking summation up to point k or less than. So yes, let's start. Here we need to find fx at x is equal to 6. So that means what? Probability that x is less than or equal to 6. Okay. So that means what? Here the minimum value start with 1 only. So it's like probability that x is equal to 1 plus probability that x is equal to 2 plus probability that x is equal to 3. Let me write probability that x is equal to 3 plus probability that x is equal to 4 plus probability that x is equal to 5 plus probability that x is equal to 6. Okay. We need to calculate this value. So, okay, it's 1 by 2 to the power k. Okay. By mistake, I have written here x. You can write x, you can write k. Okay, no problem. Also, you people, please try to solve. So, like at x is equal to 1, it comes out to be 1 by k equal to 1, plus x equal to 2, 1 by 2, plus 1 by 2 to the power 3, 1 by 2 to the power 4, 1 by 2 to the power 5, plus 1 by 2 to the power 6, because x takes value up to 6. So, now we can already solve this. It's 2, 4, 8, 16, 32, 26. So 6, sorry, not 26, 2 to the power 6, that is 64. So it's 32 plus 16 plus 8 plus 4 plus 2 plus 1. When you are going to add this, you will find it's 63 upon 64. Now, yes, 63. Two people have answered 63, obviously. So now 64 times of fx at 6 is equal to 64 into 63 upon 64 comes out to be 60. This is our required answer. Yes, the 63 is the right answer. Okay. Now the next question is, okay, try to solve the next question, okay, by yourself. This is based on the transformation of random variables. Okay. So next question is, let x be a random variable with probability density function given by, we are given probability density function of x like 3x square when x lies within 0 to 1 and 0 otherwise. This is the question. Now define a new random variable y such that y equals natural log of x. Now such that y equal to log of x. Now find the distribution function of y. Sorry, the density function of y. That is the okay. Now find the density function of y, the new random variable y. This is our question. Okay. So just solve by yourself. Again, you can see the question. The given PDF is 3x square when x lie within 0 to 1. Okay. We need to find the transformed random variable y, the distribution of the transformed random variable y, when y is defined as log of x. Okay. The simple question, as we have already discussed, since y equal to gx is there, okay, it is obviously like a monotonically, log is obviously monotonic increasing function, okay, and also it is differentiable. Log x is what? By x. Differentiable is also there. So that means we can directly apply the theorem that we have discussed. What the theorem says? We are given y equal to log of x here. So from here, x is equal to what? E to the power y. Okay. Also, we need to find the range. Okay. Since here x lie within 0 to 1, range is what? Here x lie within 0 to 1. So that means what? X is what? E to the power, na? E to the power y. We write to be small. So x can be replaced by e to the power y. So e to the power lie within 0 to 1, taking log on both sides. Log of 0, not e to the power I, it's y, it's log of 1. So let me know what is the log of 0 value. Log 0 is actually our minus infinity, you know. Okay. And log of 1 is 0. Okay. So log of, so that means what? That means y has the support minus infinity to 0. Okay. For x 0 to 1. Now we have the formula. Before that, we also need to find the dx upon dy, like d of e inverse of y upon dy. So here x is what? E to the power y. So dx upon dy comes out to be to the power y again. Okay. Okay. Someone has written 3e py. Okay. 3e to the power 3y. Okay. Minus infinity to 1. Okay. Let me check. So now we will apply the theorem directly. Okay, 0 in place of 1. Okay, okay. Let me see. Yes, obviously 0 in place of 1 because we have already find the range. Na? So minus infinity to 0, it is fixed. It is true. Now the functional value comes out to be like what? Okay. So it's fy of y equals fx of g inverse y multiplied by dx upon dy. So our function is what? Our function is 3x square. Now x can be replaced by e to the power y. So 3x can be replaced by e to the power y square into dx upon dy is e to the power y. So it's 3e to the power 2y into e to the power y. So fy comes out to be e to the power py. It's exactly, it is right. The value is minus infinity to 0. So this is the probability density function for the transformed random variable y. Okay. So is it okay up to this point? Anyone have any kind of doubt how we have calculated any values? Then you can directly ask. Okay. Okay then. If not, then we will solve next question. Okay, no problem. Anyone? No. Okay. Now the next question is okay. the distribution function of a random variable x is given by, we are given a random variable, okay? The distribution function of a random variable x is given by, we are given the distribution function. It's like 1 minus 16 upon x square for x is greater than or equal to 4, and 0 for otherwise. Okay, so this is our distribution function. Now, which of the following is true? Okay, now we have which of the following is true. Okay, so the first is like probability that x is less than or equal to 5 comes out to be 9 by 25. The second one is probability that x is greater than 8 equals to 1 by 4. The density function is 32 upon x2 for x is greater than 4. The density function of x is 4 upon x cube for x is greater than 4. Okay, you can directly see here. In C and D, there is a high 100% sure that at least one of them is wrong. I'm not claiming that it may possible that option C and option D both are like not true, both are false, but I'm 100% sure that one of them is must be false, at least. Okay, so let's solve this question. People also try to solve. The question is like this. The CDF function is given as 1 minus 16 upon x square for x is greater than or equal to 4. We need to find the probability that x is lies between x is less than or equal to 5 equal to 9 by 25. We need to check whether this statement is true or not. So, okay. So the first is probability that x is less than or equal to 5. So you know that, nah? What we know that fx is what? Probability that x is less than or equal to not x, 5, it's x. No? We take the value of x is equal to 5 here. Probability that x is less than or equal to 5. And we are given actually CDR. It's 1 minus 16 upon x square. 1 minus 16 upon x square, that is 5 square. So it's what? 1 minus 16 upon 25. So it comes out to be 9 upon 25. So that means what? This is true. That, sorry, not here, right here. So the statement 1 is true. Okay. Now the second is x is 8. Now the second statement is probability that x is greater than 8 equals 1 by 4. Okay, you people know the probability of complement. Na? The probability of complement is what? The probability of x is greater than some value k is equal to 1 minus probability that x is less than or equal to k. Okay, the complement probability is actually 1 minus the probability. So that means what? The probability that x is greater than a equal to 1 minus probability that x is less than or equal to 8. Okay. Now what? 1 minus probability that x is less than or equal to 8 is nothing but the CDF value at x is equal to 8. And we know that 1 minus our CDF value will be like 1 minus 16 upon 8 square. So it's 1 minus 1 plus 16 upon 64. So 1 will be cancelled out. 16 upon 64 comes out to be 1 by 4. So probability that x is greater than 8 comes out to be 1 by 4. So which is also true. I think it is also true. So these two sentence like statements are correct. Now the third and fourth, we need to check one. So how can we define like the CDF and PDF? Sorry, the PDF. The PDF is defined as like what? The probability function of x is actually the differential of the CDF function. Okay, this is actually the D is incorrect. Okay, okay, that means C is correct or not. We need to also check that. No? D is incorrect. That doesn't mean the C is correct. No? Okay, D is incorrect. Correct. Achha, D is correct. And 1, 2, 3 are true. Okay, Nikhil said 1, 2, 3 are true. So we have already, okay, 1 and 2 are correct. That I'm sure. C is correct also. Okay, let me check. This is the final one. What are our definition? Is 1 minus 16 upon x square. No? Our fx is what? 1 minus 16 upon x square. Okay. So we can also write like this, no? 1 minus 16 x to the power minus 2. Okay. So now fx is what? ddx of 1 minus 16 x to the power minus 2. 0 minus 16 minus 2 x to the power minus 2 minus 1, that is minus 32 x to the power minus 3. So yes, 32 upon x cube for x is greater than 4. So that means what? That means the third statement we have written here is, so undoubtedly the both are not going to be true. So it is false. Okay. Any doubt up to this question? If not, then we have some more numericals. Okay, let me write. Okay, this question I like. See, the question is like, let x be a random variable with PMF. Let x be a random variable with probability mass function. PMF is given, that is probability that x equal to x equal to 2c upon 5 to the power x for x equal to 1, 2, and so on. Okay. So this is okay. Now the question is for some constancy, obviously. Then the value of C is. So we need to calculate, find the value of C. So let's solve this first. As we know that, na, we have already discussed. For this kind of question, we directly use the probability. The sum of the probability comes out to be 1. This property we need to use. So since it is a discrete random variable, so instead of integral, we use summation. Probability that x to x comes out to be 1. So it's like what? Summation 2c upon 5 to the power x, x from 1 to infinity comes out to be 1. Okay. You people also let me know the value of C if you have solved. Okay. So let's take 2C common. It's like what? It's 1 by 5 plus 1 by 5 square plus 1 by 5 cube, so on, comes out to be 1. This is what? This is a GP, no? Geometric progression. This is an infinite series sum actually. Okay, infinite series, geometric series. So And here the value of R, the value of the rate, the ratio. Ratio is like what? The successive term divided by the previous term. So 1 by 5 square divided by 1 by 5 comes out to be 1 by 5 there. So here rate term is actually what? Is 1 by 5. So this summation is like, it's R. R is like 1 by 5 divided by 1 minus R is 1 by 5 equal to 1. So it's like 2C. Or okay, it's like 1 by 5 multiplied by like 1 minus 1 by 5 comes out to be 4 by 5. Okay, answer it comes out to be 2. Someone's answer comes out to be 2. It's 4 by, sorry, 5 by 4 equal to 1. So 5, 5 cancel out, 2, 4 cancel out, C by 2 comes out to be 1. Yes, C equal to 2 is the right answer. So Nikhil have said right. So 2, sorry, C equal to 2. This is right up to this point. Okay, now I have one more question actually. Okay, in the same question, find the probability, find the probability that X is even. Okay, X is even. You need to calculate the probability for this. See, the value of X is what? The value of X is 1, 2, 3, 4, 5, 6, and so on. Okay. So what we need to do is we need to find the probability for X is equal to even. Okay. We need to calculate the probability that X is equal to even. So is it like 1 by 2? Anyone? Let me know. So let's solve. You people, please try to solve. This is a good question. Again, you can see the question. The question is fx, like probability that x equal to x is 2c upon 5 to the power x. Okay. You need to find the probability value of c, and the value of c comes out to be 2. So that is our 4 by 5 to the power. Okay. Now our given PDF is PMF is what? See, I am already okay, 1 by 6. Someone has written 1 by 6. Okay. So it comes out to be 4 upon 5 to the power x for x is equal to 1, 2, and so on. Some other people, please you also try to solve and let me know if people have a similar kind of answer, then it's true. Okay. This is, now we need to find the probability that x is even. So probability that even. So each value is like what? Each value comes out to be like 2, 4, 6, 8, and so on. The value of x contain 2, 4, 6, and so on. Okay. So probability of even is something like this. Probability that x equal to 2 plus probability that x is equal to 4 plus 6 and 8 and so on. Okay. So now the next is what? 4 upon 5 square plus 4 upon x equal to 4, 5 to the power 4 plus 4 upon 5 to the power 6 and so on. We can take 4 as common. Okay. So 4 is taken as common. It's 1 upon 5 square plus 1 upon 5 to the power 4 plus 1 upon 5 to the power 6 and so on. Again, the geometric progression. Okay. Again, the geometric progression. So it comes out to be 4. Here, the value of R is 1 by 25. 1 by 5 is what? That is 1 by 25. So 1 by 25 upon 1 minus 1 by 25. It comes out to be 4. It's 1 by 25 multiplied by 25 is numerator, and 1 minus 1 by 25 comes out to be 24. 25 will be cancel out. 4 upon 24. So probability that x is even is nothing but 1 by 6 is the right answer. Okay. So this is the right answer up to this point. Anyone have any doubt other? Any other doubt? Okay, so let's solve one more question. This is the last question actually. Okay. The question is like to let x be a random variable. X be a random variable. X be a random variable with PDF. The PDF is like fx of x equal to 0.2 when modulus value of x is less than 1, 0.1 when modulus value of x lie within 1 to 4 and 0 otherwise. Okay, this is the question. Okay, x is a random variable and fx is defined in such a manner that if x takes the modulus value of x takes less than 1, then the probability value comes out to be 0.2. And if modulus value of x lie within 1 to 4, then it comes out to be 0.1. We need to calculate the probability or something. Okay, yes, we need to calculate the probability. Find or calculate probability that x lie within 0.5 to 1. Okay. So you people also try to solve. Take the screenshot if you want. Okay. Now the solution is like since we are given fx in modulus form, let me write in some simpler form first. So it is 0.2 when x is like minus. Okay. So it is like what? -1 to x to 1. See, x mod x lies less than 1. This implies what? X lie within -1 to +1. Okay. 0.1 here. Mod x lie within 1 to 4. This means what? This means actually it's x lie within -4 to -1 and x lie within 1 to 4. Okay. And 0 otherwise. This is the same density function actually. This is in terms of modulus and this is not. Okay. Now we need to find the probability that x lie within 0.5 to 5. Let's solve this. See, we have the probability value in different parts. So we first divide in those parts. Like this probability value can be written 0.5. Okay. So we can write this like probability that x lies in 0.5 to 1 because there is a one section. Okay. Someone said 0.4. Okay. Let me check. Okay. So 0 to -1 to 1 has a probability 0.2. Okay. So that means x lie within 0.5 to 1. This is one section plus probability that x lie within equal to, you may write equal to 4 because 1 to 4 is there, na? Because 1 to 4 has the probability 0.1 plus probability that 4 to 5 is also there. Okay. So this probability value 0.5 to 5 can be factorized or categorized in three parts actually 0.5 to 1, 1 to 4 and 4 to 5. Now what? 0.5 to 4 it has probability 0.2. So the integral value is 0.5 to 1, the integral 0.2 dx plus it's 1 to 4, it's 0.1 dx plus it's 4 to 5. There is no definition for this range. So obviously it's 0. Okay. So it's 0.2, x is there, 0.5 to 1. Let me know if you have any kind of difficulty in the integration, let me know. Okay. So it's 1. So 1, the integration of 1 is nothing but x, and the interval, sorry, yes, the limits are 0.5 and 1. Again here, it's here again 0.1 is common, and it's x is there, it's 1, it's 4, plus it's nothing but 0. Okay, so it's 0.2. So 1 minus 0.5 is there, it's 0.1, it's 4 minus 1 is there, 0 is converted to be 0. Okay, so 1 minus 0.5 comes out to be 0.5. So 0.5 into 0.2 is nothing but 0.10 or 0.1 plus 0.1 and 3. So it's 0.3. Yes, the answer is 0.4. So probability value that x lie within 0.5 to 5 is any doubt, any question up to this point? Manish typing, okay. Any other people have any kind of problem? Want to ask anything? Okay. It's see, if you have no kind of doubts, then I think I'm done with all the questions I have prepared for you people. Okay. So if there is no question asked, I think we can conclude our session here. Okay. I think Nikhil has typing something, so let me know. I'm just waiting for what you want to ask. Till then, you people have any other thing to ask? It's Satya, Nikhil, and Rashmi. Anyone have any doubt?
No, sir.
Okay. Nikhil, I think you want to ask something or something. You are typing. Okay, you both people are typing. Let me see. Okay, no, sir. Okay, Satya, thank you. And this much of time is taken by Nikhil, so I think you must have some question. No, that's it. I think we can solve a few more card or dice related problem, but then some other time. Yeah, sure. We will solve some numericals. Okay, based on dice and cards and all. Actually, we do not we didn't solve any question related to cards actually in the last like week one section, week one lecture. Okay, then definitely in next lecture, we will have some numericals based on cards at least. Okay, then okay, we will definitely solve at least some questions related to cards, and then the next week topic, perhaps I think it's moments, so we will solve those questions as well. Okay. Any other people have anything? We will solve this. Okay. I will take this query and we will solve this. I was just going to solve some. Okay. Because those can help me. Okay. Yeah, yeah, sure. Obviously, we need to solve some numericals, at least one or two numericals, or at least we need to know the distribution of cards. But Unfortunately, in the last week, we do not solve any kind of question related to cards. Okay, so we will definitely solve in the third week. Okay, I hope you will be there. Okay, then if there is no other question, then we can conclude our session here. Thank you, everyone. Few people may leave the session. So before that, let me stop the recording first.